Swayam Prabha. Digital India. Educated India.
So, the next as we said in the last class, that we have done the mass, we have done the momentum, now we are going to do the energy equation, right. Okay, so, energy balance at the interface QL double prime minus QV double prime dot N relative plus square by 2 minus EL. Okay, where in this particular form, where work done by surface tension ST and disjoining pressure is neglected. Okay. And the velocity of the reference frame is taken as the interfacial velocity VI, right. Velocity of reference frame is taken as the interfacial velocity VI. Okay. So, now this can be further written in this particular form KV. So, this is basically we are using the Fourier's law of heat conduction, right, to replace the Q this and this, right, the two flux terms, right. This you have already seen earlier. Okay. So, this equation can be further written in terms of the enthalpy. Let us go to the next one. So, in terms of enthalpy, this becomes, these are basically long equations. So, just takes the enthalpy, that is the definition for enthalpy, right. Okay. Now, based on this you can write KV is basically nothing but the Fourier's law of heat conduction terms that we have written over here. Okay. The long equations. This is the corresponding work done by the stresses. Equal to M HLV, that is the latent heat component, PV rho V minus PL rho L plus half BV square VI as half VL square plus VL into VI. Okay. So, this is basically the latent heat of vaporization. Right. Okay. Similarly, likewise we told earlier that the stress tensor is already predefined, right, Pi plus 2 mu d minus 2/3 mu, okay, into the corresponding identity. So, since the relative velocities of the interface also satisfy this condition, VL minus Vi to n must be equal to m dum prime divided by rho l, right. That is the velocity of the interface. Think about it, it is just that how much of the interface actually moves, that is basically what is taken up by the mass flux, the amount of mass that is going to the other phase. Okay. And similarly, we can write it Bv minus Vi into n is equal to m dot. Remember that this is liquid density, this is the corresponding vapor density, right. Okay. So, combining all these things together, if we write it now, PL VL minus Vi dot n minus PV VB minus Vi dot n equal to m double dot minus PV minus minus rho v minus PL divided by rho L. Okay. That is the expression, that is the form that you get, okay, if you do this kind of substitutions. Now, from the relative velocities of the interfaces you get that. Okay. Now, if you to simplify the energy equation that you have over here, this guy that you have over here, we can make several assumptions, because that is a long equation, right. Normally you do not encounter equation as large as this, right. So, how to actually make it appear a little bit simpler. So, there are two ways that you can do it. One is that if you neglect the kinetic energy terms are neglected, right, that is one way of doing it. And if you assume that there are no slip conditions at the interface, okay, by no slip condition, therefore, you mean VLT must be equal to VBT, it must be equal to VIT, right. Okay, across the interface all these velocities should be the same in the tangential direction, that is a no slip basically. Okay. So, the energy equation therefore, okay, if you apply all these cases, okay, that there is no kinetic energy change, there is no slip, etc., it becomes a perfectly manageable form, which is given by, and this I urge you to do the math, it just requires the substitution dot n, that is it, right. So, it is basically two heat conduction terms that you have, right, and the corresponding mass transfer due to evaporation or whatever, and the corresponding latent heat. Okay. So, we can arrive at this particular form of this particular equation just by making those assumptions over there. Okay. So, this is also widely used, in fact, in most of the cases you will use this, right. So, this is the conduction is equal to whatever the mass that is taken away, right, by this. Okay. Now, you can compare, you can make, you can have analogies in which you can compare the order of these two terms, and you can make assumptions that which gradient to neglect, which gradient to take, okay, and things like that. Okay. But other than that, that is what you are supposed to get. Okay. Now, before we go to the species equation, okay, and species equation comes with it a little bit of the how the phase change actually happens. Okay. Let us look at an interesting term over here. So, we will come to this thing a little later, but before that I wanted to cover the, because we are still in the momentum part of the equation, and momentum and energy we have covered. Let us look at some of the dynamic behaviors of these interfaces, because we have done this momentum balance across the interface and things like that. Let us look at the dynamic behavior of the interfaces before we go on to the species balance, and then we talk about how evaporation actually happens, right, how the slopes matters. Just now we established that there is two conduction terms basically, right, that you saw is equal to whatever is the mass that is that actually evaporates, right, from one phase to the other, right, if we neglect all the kinetic energy terms and everything, okay, which is very normal practice to neglect the kinetic energy terms, because the other terms are so much more significant, right. So, but before doing that, let us do the dynamic part of the interface, okay, which is what we are going to do in this few slides. So, this kind of examples are seen everywhere, right. Say for example, you have a vapor, right, and you have a liquid, right. Okay. So, basically by vapor and liquid means there is a very large variation in density, okay. Vapor liquid density is almost like 1000 times, right. So, what happens is that there is a layer of liquid which is sitting over a layer of vapor, right. Let us look at the problem in this particular fashion, right. There is a layer of liquid which is sitting over a layer of vapor, and both of these two are actually moving, right. So, so here there is a velocity which is uv, which is the vapor phase velocity, there is a velocity which is ul, okay, this average velocity which is in the liquid phase, okay, and there is an interface which basically separates the two, got it. Okay. Let us not talk about evaporation and all those things for the time being, okay. Let us keep this problem very simple. Now, what happens is that a physical state of this interface, okay, is said to be stable if it can withstand a disturbance and return to its original state, okay. So, if the statement is like that, means if this is the interface and I give it a spanking, that means I just perturb the interface and I create this perturbation which is delta, right. So, it is basically, you can consider it to be like a string, right, and I am basically just clipping a part of the string, right. So, it naturally will oscillate. Now, if this oscillation dies down and it returns to its original flat configuration, which is this configuration, right, then we will call that this is a stable situation, right. So, nothing happens, you impose a disturbance, the disturbance decays away, and so it is a stable configuration, okay. So, in this particular case, gravity is appearing this way, it is a horizontal pipe and you have a liquid and vapor, both of which are actually moving, right. Very common problem, okay. Need not be always liquid vapor, it can be disparate density fluids also. On the other side of it, if I just take this and if I just rotate the whole thing, okay. So, what will happen is that gravity is now favoring, appearing like this, correct, and you have a liquid velocity and you have a vapor velocity, same thing, interface is now vertical instead of horizontal, and again you perturb it and see how the perturbation actually evolves, got it, okay. So, here the parameter that we are interested in can be anything, this is phi, it can be velocity, it can be pressure, it can be temperature, it can be species also, whatever, okay. And a disturbance of this magnitude which is given by phi prime, phi with a prime, right, that is actually added. That means, when there is a velocity u, we are adding a perturbation which is u prime, right. So, and the interface gets disturbed by this magnitude which is given by delta, okay. So, the both phases we are assuming they are incompressible, they are inviscid, so that we get rid of all those viscous stress terms, and it is not, that is immiscible, that means they do not mix with each other. That means, there is no diffusion that happens, okay, in terms of one species going into another, right. So, you can think about it in this particular way, right. Okay. Now, the liquid and the vapor flows are essentially two dimensional in nature, that is another set of assumption, okay. So, based on that, what we can do is that we can write three equations, this is the mass and the two momentum, right. Why the viscous term is not there? This is because we have neglected viscosity, we have assumed that it is inviscid in nature, right. So, what we have, you have the u variation of u, this is the convective derivative, this is basically the inertial term, and this is the corresponding pressure. We have added gravity in the first case, okay, that is because of in one case in the y momentum equation, gravity enters into the picture. So, if you look at this particular equation, this is the y axis. So, gravity is acting along the y axis, correct. Okay, so that is why the gravity term is already there, right. Now, we are going to decompose the velocity. So, there are basically 3 variables, right, u, v and p, right. So, we are going to decompose the velocities and pressures into a base flow and some perturbed components, right. So, it is almost like akin to the Reynolds decomposition that we do, okay, in your turbulent flows, right. So, what happens is that you have a u bar, which is a mean or what is called the base flow, and then there is a perturbation component. V is given by V bar and a perturbation component, P is given by P bar and a perturbation component. So, everywhere there is that perturbation component, right. So, you substitute all of these things over here in this set of equations, right. So, what you get, the set of equations, and you recall that your u bar and your v bar and your p bar all satisfied the Navier-Stokes and the mass and the continuity equations, right. Okay. So, based on this substitution, you now arrive at 3 additional sets of equations, right. Okay. So, first one is basically nothing but du prime dx v prime dy, that is the continuity version of the perturbed component. Okay. You can think about it like that. Okay. The next component is this, the next component is that. Now, the products of the perturbation, and why the g actually drops down, that is because it does not have a perturbation, right. Okay. And we have assumed that the density is of course fixed. Okay. So, there is no perturbation on the property, right, that can also happen, but here we are assuming that the perturbation is not happening on the density. And the product of the perturbations, that means the prime terms are neglected, that is u prime v prime is neglected. Similarly, if there are quantities like u prime p prime, these are all neglected. Okay. So, they are all neglected, right. Okay. Now, we take this set of equation and we differentiate it with respect to x and y, right, respectively, okay, and then we sum them and we substitute the continuity equation. This yields what we call the Laplace equation for the pressure perturbation field. So, if you do this, you will get this particular equation, which is basically nothing but the pressure perturbation, or this is a Laplace, you can see that this is basically this, right. Okay. So, it is the Laplace of the pressure perturbation, okay, it is not the pressure, it is the pressure perturbation. So, that is what we have done over here. So, basically what we have done is that we have basically taken the derivative with respect to x and y, okay, and then we have substituted the continuity, we have summed them and we get the Laplace pressure field. Okay. So, this is the pressure field or the perturbed pressure field that you get, right, and the shape of the interface that we showed at any particular point of time is assumed to follow an expression like this. This is very typical linear stability type analysis that people are normally familiar with, right. So, what this has? It has basically a z component, that means the interface fluctuates in the z direction, if you look at it. Okay. So, that is the interfacial fluctuation, and there is a time component. Okay. Similarly, the postulated forms of v prime and p prime is also taken as a similar form, right, like we took in the case of delta. Okay. We took it in the case of delta, we have done a very similar thing for v prime and p prime. Okay. These are postulated forms. Okay. We are postulating that this will be the form, and then we use the corresponding Laplace. This is a 2-dimensional field. Okay. Only one curvature is needed, right. So, the P capillary pressure is what we are using over here. Okay. So, based on these postulated forms, one can show, and this is not a linear stability analysis class. So, we are not going through the detailed math of how we are arriving at this. Okay. What we get is that an expression like this, that means the square of the velocity difference between the two phases, not the perturbed, but the mean velocity square, and you have taken a modulus of that. That means you have taken a minus, taken the absolute value of that and squared it. Okay. So, it does not matter which one is positive or negative, right, which one is slow or fast, correct. Okay. So, that is given by this particular expression. Let us look at it term by term. There is a term involving sigma, which is the surface tension. There is a term involving the gravity, right. Okay. And this alpha that we have written over here is called the wave number. Okay, it is 2 pi by lambda, lambda is a wavelength. So, alpha is a wave number. Now, the surface tension and gravity, so this is surface tension term, this is gravity term, right, that is what we told. So, surface tension and gravity tends to stabilize the interface for this configuration. Okay. So, if you look at the configuration for the for this particular configuration, right, both gravity as well as surface tension tries to stabilize the interface. That means, it tries to bring the interface back to its original configuration, which is flat, right. Okay. So, both gravity and this tries to do it. Okay. So, the right side of this, and remember this is also an inequality form, right. So, this must be greater than that. Okay. So, the right side of this inequality has a minimum value, right side means this side has got a minimum value when the wave number is equal to the critical wave number, right. So, if you minimize this part, the right hand side of this equation, right, okay, what will happen is that this has a minimum, and that minimum, okay, that minimum alpha, because all other quantities, okay, so are fixed, right. So, only alpha is the variable that you have here. So, basically you minimize this quantity in terms of alpha, right. Okay, so, that critical alpha is given by this particular parameter, which is nothing but rho L minus rho V, that is the difference in density of the two phases, right, and multiplied by G divided by sigma and the root over of that, right. Okay. This sounds familiar to a certain audience, you can think about it. I will give the answer in the next class, that what does this actually resemble, right. This sigma divided with this, you can write it like this, rho L minus rho V into G and root over of that. Okay. This is an interesting quantity, okay, that is associated with this. Okay. So, what is this basically means that it is basically sigma and the corresponding gravity term essentially, right. Okay. Similarly, when you substitute this alpha critical over there, okay, in the expression, you get a critical difference, a velocity differential, right, okay, and that is given by this particular expression. Okay. For motionless liquid over motionless vapor, that means when the both the phases are actually static, right. Okay. So, this was it is actually moving, right. Now, if the vapor and the liquid phases are all motionless in nature, then alpha must be greater than alpha critical, that means it must be greater than this particular quantity. Lambda c, that is the critical wavelength, okay, is given by this particular expression, which is nothing but this particular length scale that we have here, and this perturbation, a perturbation which has a wavelength greater than this lambda c will actually grow. That means, when you have a motionless liquid sitting over a motionless vapor, what will happen is that if you perturb it, okay, with an amplitude, okay, which is greater than this particular critical wavelength, okay, this will actually grow, right. So, look at one particular thing, a perturbation greater than this wavelength, that is the key clause over here, right. So, when this rho L and rho V becomes very close to each other, right, that means you are dealing with water and something which is a little bit more denser than water, right. What will happen in that particular case, right? This lambda c will be a very large quantity, right. So, in order to perturb that particular interface, you need an exceedingly high amplitude, right, because that amplitude space is very large. Lower than this won't do anything, right. So, the perturbation needs to have a huge amplitude, okay. So, long amplitude, okay, or long wavelength essentially, right. Similarly, on the other hand, if this density difference is huge, typically what happens between liquid and vapor, right, it is a huge density difference, right. This quantity is very large, right. So, the wavelength space, if you look at it, so previously if this was the critical lambda c, right, the critical lambda c is pushed back, right, to the short wavelength regime, correct, when you actually have a large density differential, which is delta rho, correct. When it gets pushed over here to this side, okay, any wavelength which is greater than this will make the interface unstable. Previously what happened when the interface was here, right, when the critical wavelength was here, any disturbance in this regions will not be able to destabilize the interface. On the other hand, if the density difference is too large, Okay. Essentially what we will have, you will have the disturbances, okay, for of very short wavelengths also can actually grow, right. So, that is a very key takeaway point, right. Even if you do not remember anything, if you just remember this, okay, this actually shows that if the perturbation for a motionless configuration, if the perturbation is greater than this amplitude, it will grow. And you should always remember that surface tension and gravity here tries to stabilize the interface. So, you have to fight against them essentially, right, and that is what exactly what you are doing over here by making your wavelength greater than that, right. So, this particular thing is called, it has got a celebrated name, it is called the Rayleigh-Taylor instability. Okay, it is called the Rayleigh-Taylor instability. So, you can have a recap. We actually have a flat interface, okay, with two fluids moving on both sides. We add a perturbation component to the whole thing, right. We decompose it into two components, I mean into a mean flow or a base flow and a perturbation part, and then if we differentiate the equations and do some math, basically it is just a tool and it is very standard these days. Okay. You get a Laplace of the pressure field and then you assume forms of delta, the pressure field and the velocity field, and then you add the interfacial conditions, which is basically nothing but the capillary pressure, right, and then you can show that what the velocity difference should be, right, okay, for a flow to get unstable, right. And for motionless configuration, okay, the perturbation needs to have an amplitude which is greater than the this, got it. Okay. So, Rayleigh-Taylor instability is seen in many cases, okay, not just in one case, it is seen in multiple fields. Okay. Now, this is Rayleigh-Taylor. Okay. Also we can define something called see the right hand side, you can also maximize it, right. So, you get a maximum alpha and then you get an lambda d, which is called the most dangerous wavelength, basically the wavelength that grows the fastest, right. So, that is actually root over 3, that is approximately 1.7 of lambda c, okay, of the critical. So, it is about 1.7 times. If you are perturbing it at that amplitude, the perturbations will grow, okay, very rapidly. Now, in these cases the gravity was it was perpendicular to the flow direction, right. In the case of the other configuration, the vertical flow, you actually have gravity which is in the direction of the flow. In that particular case you can show this, okay, and there gravity does not have a significant effect on the pressure of the phases. So, there you have this particular expression is satisfied, okay. So, it is basically UL minus UV square, on this side is only surface tension now which plays a role, right, okay, which opposes. Okay. So, a condition for an unstable interface is therefore this particular type of interface which is a vertical and gravity is actually in the direction of the flow, it is basically called Kelvin-Helmholtz instability. Okay. So, one is a Rayleigh-Taylor instability, this is a Kelvin-Helmholtz instability, both are very similar, it is just the configuration difference, which way the gravity is pointing, okay. That is what actually leads to this kind of configurations, right. So, you get an idea that when you have an interface, okay, it is basically the force balance across the interface, not only just the static force balance, right, it is also the dynamic behavior of the interface that is very important, because when you do heat and mass transfer analysis, especially say you take the configuration when a droplet is a liquid droplet, right, when it is put into a flow of air, right, what happens? The droplet actually should get perturbed. This is an interface between droplet and the liquid and the air, right, okay, and there is a flow, there is a recirculation inside the droplet, there is a flow outside, right, and there is a huge difference in density, this delta rho is large, right. So, naturally you will develop waves on the droplet surface, right, and these waves can actually lead to this KH type instabilities. That is in fact what you see in your atomization type of studies, that there are surface waves that are created and this actually ultimately leads to breakup, because when these waves actually grow, right, they will grow, right, because that is the most dangerous wavelength, right. So, they will grow and then they can actually break, Okay. So, they can actually atomize, okay, and give rise to small satellite droplets. Got it? Okay. So, this is an important exercise, that is because we showed the dynamic nature of the interface now, we showed the static nature of the interface, okay, and we covered all the equations, the relevant equations that goes with it. Okay. And after, so in the next class what we will try to do is that we are going to try to see that how the species balance now can be entered into the picture, and we will look at the mass transfer, the mass and heat transfer side of things. This we have looked from the force balance point of view, that how the, so these interfaces actually do not actually evaporate, this example that I showed over here. Okay. So, in the next class we will try to do the species balance and move from there. Thank you.